Hi. So let's move on to lesson 3. This is nonlinear static buckling. So this is interesting. We do have buckling in simulation professional, and we might think that it is the ultimate one, but frankly, what it is called as something like linear buckling over there. So the assumptions are in the linear range, as well as the considerations to the change in stiffness of the geometry when we change the rather when the forces are leading to change in the geometric details are not considered in linear buckling. So in nonlinear analysis, we can actually do a more accurate analysis and understand the buckling load. It could be as simple as a linear analysis, but a bit more detailed to understand at what point the buckling happens. So this chapter will give us a good understanding on how to capture it. As well, in the last chapter we studied two different algorithms for nonlinear convergence. One was force, or what is called as loading based control, and the other one was more result oriented control. In this chapter we'll see something called as arc control, arc length method to control the details of the setup. Let's move on. So as I said, in this one we'll see or do a nonlinear analysis with large deformations. Obviously buckling will have large deformations, and buckling analysis. Define controls for a nonlinear buckling analysis, but using arc length control method. Compare the results between these things, that is linear buckling and nonlinear studies. Understand the influence of initial disturbances on the buckling of the symmetry. So let's understand if there are any initial disturbances, how the results can change, or what could be the kind of difference. Okay. Let's move on. So this is a study wherein the part is is something like this, as that shown on the screen. It is more of a kind of a roof. If I show you this, it looks like this in the software. You can see here. So it's a kind of roof wherein we are only taking the top four faces for analysis. We are not taking the entire setup, and again we can see enough symmetry here, so we can actually take only the quarter model for analysis, and that is what is done here, and we do the analysis for only this particular 1/4 model. Okay. Of course, we are doing a nonlinear full analysis, as that what you see here, and we'll see why we go into that. So so some parameters have been defined here in terms of radius, thickness, width, etc. So those are there. Initially we will do a linear buckling analysis. I believe most of you are comfortable with that from what we learned in simulation professional. So the top surface is defined as shell element here. It has a thin shell with a thickness of 6.35 millimeters. We have simply supported edges. So remember, shell is there, and we are using immovable, no translation. So rotational degree of freedom is free. It can rotate. Symmetry is being defined on the other two edges. Okay. Force is applied on the central point of this particular top surface. Okay. A force of 250 Newton has been applied, so the multiplication factor will give us the result. On solving this, the result, we are getting a multiplication factor of 27.88, and you can see that that whatever is the multiplication factor, we should be getting the maximum load required, or the load at which the buckling may be happening. We are going to deal and discuss this in more detail, wherein we are talking about whether symmetricity is making a difference, whether to use symmetric models for buckling analysis, why to be used. But in this case, in this moment, you can realize that this particular model is a quarter symmetry model. Number two, the loading is absolutely at the central point, so it's okay to use symmetry. However, remember the result. We'll discuss more in detail in this topic, but that's what it is. We got a multiplication factor of 27. So I believe I'll not go deep into these steps. You should be comfortable from whatever we learned in simulation professional. So this is how it goes for the linear buckling analysis. Factor is 27. Yeah. So the force, when we multiply, it is in the tune of 27 1800. I think the multiplication factor is a little bit different. That's fine, but that can be changed or checked. Let me check per. Okay, this is per item is 250 newtons. So for the entire model, it would be 4 times of that. That is fine. Okay. Now moving on to or discussing a little bit on linear buckling. So as I mentioned, there is an assumption in linear buckling that the structure does not exhibit significant changes prior to the onset of buckling. Okay, remember this word. So definitely it's a different concept defined by limiting step to etc. Therefore, the results are far more conservative, far more on the conservative side. And of course, we are not studying the post-buckling behavior. Once the buckling is done, we stop there. We just know the force at which the buckling is happening. Okay. Thereon, let's just for the understanding purpose, we can create a simple structural analysis wherein similar loads have been applied, simply supported edges, symmetry is taken into consideration, 240 Newton load is applied, and a displacement analysis is done. So this analysis will give you a feel of what is the kind of deflections that one can expect at 250 Newton. This is required a little bit later. I'll tell you why, and we'll look into it. Of course, you can notice that the maximum deflection is hardly 0.5 millimeters in this linear static analysis. Okay, remember that. Now we are looking into nonlinear analysis, and we are making use of or taking the advantage of symmetry over here. Let me first go into the setup, how it looks. So if I take nonlinear analysis setup, the setup is something like this. Typically shell, similar to that. Simply supported, same, symmetry same, the load is applied in the same way. So just the same as we did in linear buckling and linear stress analysis. Okay, both were linear. But when it comes to the properties, there are a few different changes that have been done. First of all, remember when we select arc length, that's what is being done in this setup. The time values that are present here have no relevance. Okay, no relevance. So these are there, but you can neglect it. Definitely this is a large displacement formulation, so that has been selected. Direct sparse, that is fine. So in the control methods, we are selecting arc length method, and appropriately it will expect certain parameters down here. Now we'll deal or discuss a little bit more on these, but before that, just remember we are giving the maximum load pattern multiplier. So this could be the worst case, I can say, where maximum deflections can happen. We are giving the expected maximum displacement value. We will look into the training manual where we say how we arrive at this value. Maximum number of arc steps. So obviously this will help us define the accuracy or how much we are willing to lean back or move around the given on the graph of the post buckling analysis, and the initial arc length multiplier. Now frankly, it is difficult to come up to these values easily. You can leave them at these values. Maximum displacement can be interpreted. This is typically 1E8, so these two are almost decided, and it's no harm in giving this value on the higher side. Obviously, these two would lead to or affect the accuracy, so you may be a bit cautious. But difficult to decide these values in the sense you cannot start off knowing the exact values initially. Okay, but we'll discuss a little bit more on this topic. Apart from that, we are in the result options. We are giving the stresses. We are deciding what we want to capture in the form of a graph. There is a sensor which is created, a workflow sensitive sensor, which is typically or is at the center of this point, and we are saying capture the stresses and strains at all the steps. So nonlinear analysis gives this result option wherein we can say what you want to capture, when you want to capture. Obviously this will help in reducing the file size. You can decide what kind of or control the maximum file size that one wants to use. Let's move on, or before that, let's go into this training manual, see it in a bit more detail. So as I told you, these time have no relevance here, so those can be neglected. We are specifying these arc length completion options, so those have been specified. What else is relevant here? Okay, so as I mentioned about the arc length parameters, that is what is being discussed here. Um, it is as I told you, it is difficult to interpret or know these options easily. So it is therefore recommended to keep the initial arc length multiplier at 1 and maximum equal to and the max multiplier at 0.1. When the equilibrium path is plotted, we can, so obviously once a particular solution is done, you can plot the equilibrium path at the workflow sensitive sensor or the location, and that can help us judge on the right values for these things. So if you quickly see at these three different graphs down here, one is this one, which is at I think 20. Let me check. Yeah, but at the moment just see these graphs and the triangles that are available here. Obviously the second one, B option, is far more accurate, and C is definitely capturing the entire scenario. And of course the maximum displacement is stopping at 30 because we are limited it. We can actually solve it further up to yield limit as well and further to that. So let's have a quick discussion on this. First one is using the initial arc length multiplier at 1. So rather all three have 1, so that continues as it is. Max, initially it is 1, 0.1 and 0.01. So this is the maximum time step that it is taking, and maximum number of arcs is moving from 20, 500 and up to 1000. So obviously C is the most accurate one. That tells. Definitely we see the top graph, it appears A could be a bit coarse analysis. I want far more accurate, so B sounds good. C would be very accurate, which may not be necessary, but if just to get a feel of how it looks, you can do this analysis. So all said and done, it is difficult to interpret these parameters before we start off doing some coarse analysis. So better do it and then get a good feel of it. And what else under advanced options? These are done. Yes, the estimated maximum displacement, in this case what we are given as 30, can be interpreted using this formula. As I said, it does not matter if you give it a bit more, but giving this value would stop the solution. That would be easier. Okay, so in this case we can see the formula. It is 2 times the linear buckling factor multiplied by maximum displacement from a static study. So we are getting certain displacement from the static. So probably you are doing the static analysis for this reason as well. So you can get a grasp of what could be the maximum displacements that can come at a certain given load. So this is the way it goes on. Using that we are getting the factor to be 20. Obviously the buckling load multiplier is going to give us, or I think the equation is self-interpretatory, but if it has to be done blindly, then you can just use this formula. Results option I showed you. Run the study, you will get the results. We analyze the section. Yeah, so obviously we have stopped it at 30 millimeters. That's what we said. It can stop either at 30 millimeters or when the number of arcs reach the maximum value of 100. So it can stop at because of any one of these two reasons. And in this case, the maximum number of arc steps was as well reached. Animate displacements, yes, we can always do that, and of course the response graphs would be far more relevant. So in this case, if I go back here, it is rather already created. You can use it. If you don't know how to create, right click results, time history plot, select the predefined location, that this is the location coming from the workflow sensitive sensor. You can decide the results that you want to capture and just plot it. Okay, and if I take the graph, it looks something like this. So you can see many things have happened over here at the center, wherein the displacement has gone up until a certain point, which is almost 13 millimeters, and thereon, or the load multiplying factor is around 13. Thereon it slowly drops down. So this is funny, wherein it could not on increasing the load. Actually, there was rather it was observed that there was a drop in the load factor, whereas the displacement went on increasing. This is a kind of buckling phenomenon wherein actually the displacement is shooted up, I would say shooted up. However, the load required has dropped down. So if you observe somewhere from this point, let me take the text here. Yeah, from this point to this point, actually the load is dropping all the way, and rather it drops further all the way till here. This is the minimum one, I would say, and to extent it is almost reaching zero, and there on it again starts stiffening and it goes up. So all the funny things are happening somewhere here, which can be seen as the buckling phenomenon, or buckling has happened here and we are studying the post buckling phenomenon all the way after this. Okay, so using that we are capturing the behavior of that point after it has buckled. We are seeing how it works. Obviously this is the buckling point. The loads gone need to be reduced for stability. If it remains, then obviously it is crushed off, the part has failed. So for analysis purpose we are reducing the loads using the arc length method, and thereon after a certain point it is going to increase again. That is, after it has reached a certain displacement, it is observed that the part becomes stiff again and it again starts with its further path. Now it might go ahead in this way and fail after yielding of the part. That is a different kind of failure. So this is what can be interpreted. This is rather, we are doing all this analysis for getting this graph, which can be seen as a post buckling analysis. Okay, so this is what we do in terms of the same points which I mentioned have been discussed in more detail here. That is, point 1 is the point where the buckling starts, and we can see it is around 13.1 here, 13.1, which corresponds to 13,000 newtons, whereas the buckling load factor that we got was around 27, so almost 2 times, or this value is almost 50% of what we saw in the linear buckling analysis. So that tells you how conservative a simulation professional analysis is, or how much it could be, how can I say, how much it could be away from reality. Okay. However, that option is there. It can give a good feel of the buckling failures. Point two is somewhere here, right? As shown on the graph, it is characterized by a further decrease. So it continues to decrease further. Of the applied, it continues. As I told you, 0.3, 4 are there, but at 0.4 it starts stiffening again, and it further continues. Now, obviously, as I told you, we are using symmetry over here, and we have got a buckling load factor of 13.1 as well as the graph that you saw there. But obviously this is true for absolute symmetry, and which is a rare condition in practical reality. So at that point, at the point where the buckling happens, thereon, based on the model details, based on the loading details, the part can either have a symmetric nature or as well as asymmetric nature, wherein it can divert in any way. And to best understand it, this particular analysis has been done further. Let me open that setup, wherein we are actually taking the full configuration. We are not taking the symmetry configuration. Thereon, a small split surface has been created here. If you observe this pink surface, that is the one, and the load is not applied at the center, but the load is applied a bit away from the center. A small gap has been created, and if I see, it is hardly 1 millimeter, 1.5 millimeter away from the center. And if I directly jump onto the results, you can see here the graph completely changes. So this is what I'm saying. Number one, this can be captured only obviously with that small split surface or loading change. The location of force has led to a thought that symmetry is not present in the model, so obviously we need to take the complete model, and thereon the behavior of the post buckling behavior is very different, and that's what you can observe down here. Rather, the buckling values over here have dropped further, and it has gone below 10 or somewhere around 11 we can consider. So obviously it is different from 13 what we saw in the nonlinear buckling with symmetric conditions. So understand this fact. Nonlinear buckling needs to be considered very sensitively, especially in practical, and this example gives you a good feel of what could go wrong or what differences can it make based on the kind of input that we are giving. Okay. So all other things in this remain the same. Applying mesh control, yeah. For such small entities, obviously mesh control is required. Ensure that the mesh is captured properly by applying a local mesh control, which has been given down here. You can see on that surface has been selected, and a mesh control has been given on that. Okay. Sorry. Where was SolidWorks? Yeah, here it is. PDF. Set the results option, all remains the same. We see the results, plot the response graph. So this is what we saw. So over here, yeah, as I told you, it is around 11.6. Obviously, this is definitely more, can be said as more accurate. It is not because it is falling, but we are actually considering the real things. And of course, if you are interested, you can increase the number of arc steps and go in for a more accurate understanding of the details. So definitely linear buckling overestimated the buckling failure. There on non-linear was required, and finally we saw if we did not consider symmetry and we took the actual model, the results were far more different. Okay, so be aware of this fact and treat it appropriately. As well, we got a feel of the linear analysis and how it can be used to find out the maximum displacement that a non-linear buckling can experience. Okay, so advantage, obviously arc length, you can see wherever such weird, funny or huge deflections are happening, wherein the graph moves from positive to negative and further, obviously only arc length method can capture such kind of deflections. So all huge deformations, deflection analysis, it is not only buckling but any other analysis, you can use arc length. It has its own limitations, which you'll get to know when you do the analysis, but this is what it is. It can capture such random behavior of the movement of the displacements. As well, if I talk about what did I want to say? I'm sorry. Linear is done, non-linear is done. Yeah, I think pretty much that's it. That's it. So this is what it is about. Yeah, what I wanted to highlight was, so even though we are looking at arc length method here, it does not mean it is restricted to buckling analysis. It can be used for many different purposes, but this is one of the applications. This gives you a good feel, not only of arc length, symmetric models, when to use, when not to use, and how sensitive it can be, as well as those details. Yeah. The exercises given in this are very good. Please explore it, go through it. That can be of use. Okay. And what else in this chapter? I think, yeah, pretty much that's it. Okay, so this gives you a good feel. In the next chapter, that is lesson 4, we are going to move into plastic deformations. Okay, how to simulate it and how it works. Thank you for listening. Let's move on to the next video.